All right, so today we are looking at chapter 6. We're going to do the first section of chapter 6 today, looking at work. Okay, this particular section, this first section, will not be very long because we are just looking at the definition of work. Okay, so, all right, so work that's done. So when you think about work, you think about working on a problem or doing homework or doing something of that nature. But the definition of work for physics is that you have to apply a force and that the object has to move. So those are the two main characteristics for our definition of work. Work has only been done when you apply a force and when there is movement in the direction that the force is applied. So you have to move, apply a force, and you have to move in the same direction. All right. So work is always measured in units of joules, and this is our equation for work. It's just force times distance. All right, so there's our equation. Let's move on. The figure below illustrates work being done as a force pushes a box through a displacement. And notice we're having to apply a force to the box. You can see here, here's our force applied, but that's not enough for work to be done. You have to apply the force and then the box actually has to move in order to be considered actual work. Okay? And again, we're measuring that force or measuring that work in units of joules, which is a Newton times a meter. So you can see here in this table just some joules for different amounts of work that's done. So you can see that the number is so melting an ice cube, 10 to the fourth, human heartbeat, 0.5 joules. Turning a page in the book is 1,000th of a joule. So it's a pretty modest amount of work. Moving on. So if you have to have displacement and you have to have a force applied, then of course no work is done when you're just holding an object. It has to move through a particular displacement. Okay, so since the suitcase doesn't move, there's no work done, regardless of how hard it is to hold that suitcase in place. Okay, so if the suitcase does not move, you are not doing work, regardless of what your arms might be telling you as far as you're getting tired or sweating or whatever. You have to have the force and the displacement. So if you just have one, then that is not considered work. All right, so we calculate work just by multiplying force times displacement. And that works really easily when you're going in the same direction. It's literally force times displacement. But what about if the force is applied at an angle? So as in this little rolly suitcase. So your force applied is here, but the direction of your motion is here. Okay, so it's going to be a little different. You can't just multiply the two together. You have to consider the angle with which the motion is applied, with which the force is applied, and then, of course, the direction that it moves. Okay, so we'll have to come up with a new formula that incorporates the angle with which you applied that force. And this is the formula we're going to be looking at. Force times distance times the cosine of theta. So if you think about our previous slide, okay, that angle right there, cosine, remember, is adjacent over hypotenuse. So we'll know the force. So the amount of force that goes in the actual horizontal direction, which is what is contributing to the work, is going to be adjacent over hypotenuse, which is cosine of theta. Okay. So that's why we have this particular formula for work when work is done at an angle. Force times distance times the cosine of theta. because that takes into account the amount of force that is actually applied in the direction of motion. Okay, so here's a couple more examples. Remember, work can be positive, negative, or zero. Just depends on the force that's applied and then what direction that displacement is. So work is positive if the force has a component in the direction of motion. So for this example, actually, if we go back to this one, so this is our force. So we'll have a component here and we'll have a component here. So that component of force is the component that will contribute to work being positive, and it's going in the same direction as the direction of motion. So then that work will be positive. Work will be zero if it has no component in the force of direction. So this is going straight up. It does not have a component in the same direction as the motion. And then, of course, work would be negative is if the force has a component in the opposite direction. So if we look this, that angle, okay, then that's going in the opposite direction of the direction of motion. So work will be negative. Let's go back up here and think about this one. Since technically you think, oh, well, that has a component here and here, I can break that up. But remember, that it's the cosine of the angle. So if we look at what the cosine of 90 degrees is, come on, there we go. So 90 cosine is zero. So the cosine of 90 degrees, which this would be 90 degrees, that's zero. So again, you would have zero work being done. All right. When more than one force acts on an object, then the work done is the sum of all the work done by each individual force. So if we have force number one, it does work number one, force number two does work two, force three does work three. To find the total work done on that object, we would simply just add all three of those together. So when work is done on an object, you change that object's energy. So if you're pushing a shopping cart, you're doing work on that shopping cart because you're applying a force and it's moving, but you are also increasing that shopping cart's kinetic energy because now it's moving. You climb a mountain, your work goes into increasing your potential energy. Because remember, potential energy is just the energy is just based on how far above the earth you are. So if you're at the top of a mountain versus the bottom of the mountain, you have more potential energy at the top because you're further from the surface of the earth. So when you do work, whether it's climbing a mountain or pushing a shopping cart, you are changing that object's energy. So kinetic energy is the energy of motion. Remember, potential energy is the energy of position. Oh, okay. And that is where we're going to stop because that is getting into the second section.